Good afternoon. So my name is Bill Geyer. I'm the Tread Heli maintainer, and you're probably wondering why I'm giving a brief on plane and quad plane. It's all because of the system ID work and analytic tune work that I've been doing over the past year and a half. And so it's wanted to get this conveyed into plane and quad plane, so those folks can take advantage of it as well. First of all, big thanks to Peter Barker and Tridge. Peter for gathering some data and going out with his Bixler shown there to grab some data for me to show here. All right, so what I'm going to talk about today is how we've implemented System ID into plane and quad plane, how to use it, what a good frequency response characteristics look like for a good tune. I'll briefly talk about theory, and hopefully if we have time, do a little bit of a demo. So, the way we've implemented System ID in plane and quad plane is pretty different than how it's done in Copter and Heli. Copter and Heli does it as a flight mode that basically has stabilize underneath of it, and then the chirp is put on top of into that stabilize mode, but it's based off of stabilize. Whereas in plane and quad plane, it was desired that we go with it as a feature that can be started through an aux function. And so that aux function is 184 for the RC function. So it's designed to run on top of flight modes, both in quad plane and plane. And for quad plane in the VTOL, it's going to be Q stabilize, Q hover, and Q loiter that you can run the System ID feature on top of. For plane and quad plane in fixed wing mode, they are using fly-by-wire alpha, loiter, and I'm going to implement guided and potentially auto mode as well, once we see how well it does, but that's the goal. And based on feedback I got from Peter Barker and Tridge. So plane and quad plane in fixed wing, in a fixed wing flight, it's the System ID feature is only available for pitch and roll. It was felt that yaw wasn't as necessary for the fixed wing flight modes, and so basically that's all we've implemented into. As far as logging, we have VTOL uses the same logging as Copter, so there's no change there, and it helps with the analytic tune feature. And for plane, we've added a special logging message to help capture the needed signals for the pitch and roll tuning. As far as the flight code status, the quad plane System ID feature has been implemented into quad plane for the VTOL mode, already merged into 4.7 or for master, and we've actually backported it to 4.6, so it's available there as well. For the plane and quad plane and fixed wing, we're nearing completion. I have a few minor changes to make, put the additional modes in for the fixed wing flight, as well as some minor changes to some logging. But ultimately, for plane and quad plane, they use the same library and parameters for the chirp and how it's generated for the frequency sweep. And so those are the parameters there. So the SID axis parameter is kind of how you start things off. That identifies what axis you're going to be doing the chirp in, as well as where you're going to inject that chirp within the flight controls. The magnitude is the amplitude of the oscillation that it's going to make. You have the starting frequency and the stopping frequency. So you want to design those, well, first of all, magnitude, let me go over that. Like magnitude, really what I've found as far as the input angles, you really don't need anything larger than 5 degrees. You could actually probably go a little lower if you want. 15 degrees is way too high. And you might be saturating things if you have too high of angles put in there. So best to go a little smaller. 5 degrees is a good starting point. If you don't like that, stop the chirp and make it a little lower. For the start and stop frequencies, I've normally used half a hertz is great. The default, I think 15 hertz, maybe 20 at max for the vehicles that I've looked at. Something like Andy Piper small quads, you might have to go to 40, but something like a 600 size heli or larger like quad plane and planes, you probably don't have to go as high. The record length that can change. That's the SID T rec. The length of the record could be, uh, you know, 70 seconds is default. You can go lower, maybe 40 seconds. And that's kind of a crucial thing with plane because when you're flying 15 meters per second or 20 meters per second, you're going to cover a lot of ground in 40 seconds or 70 seconds. So I have ideas on how to mitigate that. That's why in auto mode, that's kind of nice. You could set up auto mode. That's why you're not worried about, you can always recall it and you can always set it on a straight shot to get the data you need through using that. Fade in and fade out, basically it linearly increases for fade in, it linearly increase the amplitude up to the max amplitude, and then fade out linearly decreases it at the end. Fade out, I normally set to like 1 second. Fade in, 5 to 15 seconds is fine. Normally, you might want to set it longer if you have lower frequencies and you're seeing that your aircraft's starting to drift a lot and you want to kind of limit the drifting. You can set that fade in to kind of limit that. Here's the laundry list of SID axis options. You can see for the different vehicle types there. You can notice that copter, heli, and quad plane VTOL are the same there for up to the SID axis 13. And then copter and heli include velocity and position controller options, where quad plane does not. And then for quad plane and plane and fixed wing mode, we only have the two for each of the roll and pitch axes. So you have the input angle and you have the mixer. And I'll go over these here in the next chart. This is taken straight out of the System ID wiki. And so you can see the control laws for all axes, actually pitch, roll, and yaw here. And so here's the input where the pilot makes the input. Here's like the input shaping and attitude controller here. Then you move into the rate controller, which is your PID and feed forward D. And then you finally get to the motor mixer and the aircraft. And then you have your control feedback loops. So for the first input angle, with feed forward enable, that's made here. And then I'm showing the same diagram here. I didn't want to show a different diagram, but this is actually the feed forward diagram. It's also made at this point, except you don't have the feed forward. It's disabled for the recovery angle SID axis option. Next, you can put it as an input into the rate controller if you want to do that. And then lastly, you can put it as an input into the mixer. And this is kind of good if you're going to do a system identification of a vehicle model, or maybe you're doing something like a broken loop stability type analysis. For the fixed wing, this is a generic, I took this out of the wiki as well. And this is a generic diagram for the control laws for one axis of the fixed wing aircraft. So pitch or roll, your choice here. But here's where the input angle SID option is. The SID axis is here at where the pilot makes its input, and then for the mixer, it's down here right before it goes into the mixer. So, and again, I added this so that you could do system identification of a quad of your airplane and have that data available. All right, so how to use it. So in pre-flight, there's a number of steps you got to go through. First of all, the big thing is that this feature is not built into the standard build for plane or quad plane. So you have to use the custom firmware builder to compile the code and include that system ID feature. Right now, if you go there and you look under the plane category, you'll see system ID support for quad plane. That will probably change in the near future and say system ID just general in the and then that will cover both quad plane and fixed wing. And then you load that on your controller. You modify your SID axis parameter initially. You have to make that input as to what SID axis you're going to use. You you write the parameters and then reload the parameters and then or refresh them, and then you'll be able to get the rest of the settings that you'll be able to make. I guess I would recommend input angle for fixed wing tuning and recovery angle for VTOL. And Andy Piper and I found out that if you have an angle P greater than 10, his was like 24, and it made very large inputs. So don't use recovery angle if you've got very large angle P's. Use the input angle instead. And then another key feature or key thing here to mention is for plane, the scheduled loop rate is actually 50 hertz by default. And so I would recommend you change that to 100 hertz so that the minimum logging is at 100 hertz. And I would recommend you just keep it there, because once you do your analytic tune, you don't want to degrade your loop rate to 50 hertz again when you've tuned it with the loop rate at 100 hertz. And then what that feeds into is that the log bit mask sets that logging rate, and it's a combination of fast attitude and medium attitude. If you want it at the full loop rate for your logging, then you'd have checked both fast attitude and medium attitude. I think that's the best way to go. Just check those. It's more data is better, and I don't think you have a problem with running out of space. Set RC function to system ID number 184, and then put it on a switch so that you can invoke it from your controller. All right, how to use it in flight. So you'll take off, climb to a safe height. If you're using quad plane in a VTOL mode, it's just like multi-rotor or heli, where you're just going to hold a constant height. You'll be in loiter, Q loiter, Q stabilize. I can't remember the other one. Q hover, and you'll implement that. For plane and quad plane and fixed wing flight, you really need to, so it's important to hold a constant height and a constant speed. And the reason for that is because there's scaling that occurs. And I believe the parameters like A speed, or the variable is A speed, that's used. And then there's an airspeed conversion, that's the EAS to TAS, which I think is kind of a conversion of the pedostatics to true airspeed. And so that you definitely need to have those constant, because I have to average those over the run. And if they're not constant, then that could affect the quality of the analytic tune you're going to try to do. You'll enable the system ID feature through the aux function. So once you're up there and you're steady and ready to go, you'll flip the switch, and you can see over here to the right, you'll see that it starts doing the oscillations. This one's done in pitch. And you'll notice that for plane, kind of a big feature here is I have this in loiter, and I've set a fairly large radius to the loiter so that the aircraft roll angle isn't much greater than 10 degrees. I found that you could probably get away with around 10 degrees roll attitude for a pitch frequency sweep, and even for a roll frequency sweep, so that it kind of keeps it in orbit above you and closer to you. But again, that all depends on speed, right? That angle has to get larger if you're going faster speeds. The radius to maintain 10 degrees would have to get larger as you have faster speeds. Once your chirp is complete, you'll either be told through your ground control station, or if you just set a timer and then stop it after, or flip your switch off after the timer ends, then you'll be done. Big thing here, right? Must have a stable initial tune. If you see that your aircraft starts to go, high oscillations, then you want to stop the system ID, and then try to figure out what's going on, get a better tune. You're probably got some instability that you're exciting. Quick frequency to time domain to frequency domain, because if we get to analytic tune, we need that for that discussion. So in analytic tune, we talk about two things: gain and phase across a number of frequencies. So the gain is the output amplitude to the input amplitude, as shown over here for a constant frequency oscillation. So there's my output amplitude B, input amplitude A. I do the ratio of those two, and that gives me my amplitude ratio. I could do that in decibels. It's just a conversion that's done there. And then the phase describes kind of the comparison of the peaks in time for a given frequency. And so kind of in most cases, you're going to see that the peak oscillation input will occur after, or the output will occur after the input, as shown here, and that take that time. And since it's a constant frequency, then we can determine what that phase is. And so that leads you to the Bode plot, which then shows the gain or the amplitude ratio as a function of frequency and the phase as a function of frequency. The goal here is, when tuning, is to make sure that your output is equal to your input, which for decibels is 0, so it's a 1-to-1 output to input. And then, as with anything, like if you were to drive your car, you've noticed with your aircraft, as you make higher frequencies inputs, you'll see that the aircraft does not respond as quickly or does not respond as much as amplitude. And that's what basically this is showing. As you go up in frequency, the amplitude starts to drop off of the output, and the phase starts to get worse, that it starts falling behind the actual input of the input signal. So what defines a good tune? This is Peter's data for the pixeler in the pitch axis. And so you can see this is the calculated frequency response for attitude. So we want the actual attitudes to match closely to desired attitudes, meaning that you want this to run at the 0 dB as high as frequency as possible. Good disturbance rejection, little to no overshoots. That means that you don't want this to bump up above 0 dB. Otherwise, that means you got more output than you have input. And then you want the response to remain in phase with the desired input. So basically, you want 0 phase as far out as you can. And so I did a little playing in Analytic Tune, and this is what I found with some settings. I was able to get it to stay to 0 dB all the way out to about 3 hertz. And I was able to keep better in phase out to maybe 0.7 hertz. Real quick about theory. So this is Analytic Tune, basically takes and looks at, determines the bare airframe dynamics, and then analytically wraps around the control loops. And so based on linear system theory, and essentially if you have any rate or acceleration limits, that'll affect linearity. If you have anything like slew limiting and it's actually being invoked while the frequency sweep is going on, then that will also cause problems, and you won't have a good comparison between the input, the calculated, and the actual predicted. And so real quick, I'll just jump over and just show a quick, here's the tool. This version's not up there yet, but basically you could choose your data. Once you choose your data, you then, you have your start and stop time. You can modify that, but really you're just going to choose the sit axis run that you did. So he did 2 of them. One was roll angle and one was pitch angle. I'm just going to choose pitch. Come on. And then I'll go ahead, and you have to hit calculate down here to get it to do the analysis, and then that puts out the comparison. So the big thing to do once you start this is initially with your settings, when you first get into it, you just want to make sure that the prediction matches the calculated pretty closely out to when you start seeing a low coherence. When this gets below 0.6, then you have low coherence, and you're going to expect that the output won't closely match the input. So that's the litmus test initially, and then you can start making changes to your gains up here to then change the response and what it looks like. So I lowered this guy a little bit. I think I lowered this guy some, and then I definitely lowered this a lot. And then when I go to attitude, the attitude plot, you can see there now it matches the gain is around 0 dB. I think that's all I have time for. I guess I'll stop there and take any questions if there's any questions.
Hi. Are there any plans to also backport this to Arduino Pilot 4.6 once you are done with the Arduino Plane, 4.6?
I guess that would be up to Tridge, but I don't know if we will. I think we'd probably wait until 4.7 comes out, but I'd probably push that to Tridge to answer that question.
Okay. And are the results like you get from a 4.7 like test usable in 4.6?
Yeah, I would imagine that the results would be acceptable because I don't believe there's any large changes to the control law structure between 4.7 and 4.6, or there probably won't be.
Great, thanks.
Mm-hmm.
Okay, thank you very much, Bill. One more round of applause, please.
Thanks, everybody.
Thank you for joining us for the Arduino Pilot Developers Conference 2025. With thanks to our sponsors, 3DXR, Aerosystems West, CUAV, QPilot, High-Tech, Polybro, IR Lock, KH Unmanned, Kraus Hamdani Aerospace, Maytech, Modal AI, Northwest Blue, SD Model, and Theseus. Organised by KH Unmanned. Hosted by 3DXR in North Yorkshire. Broadcast by Q Branch.